Hello there, and welcome to Bedtime Universe. Tonight, we turn our eyes and our curiosity toward one of the rarest discoveries of our age. A faint traveler slipping through our skies, a quiet messenger that did not grow up beneath our Sunday. Astronomers have given it a name you may soon learn to recognize: 3I Atlas. It is not a comet of the familiar family that circles our star. It is an object from somewhere else entirely. Another stellar neighborhood, another time, another set of conditions that shaped its dust and ice. For a brief while, by chance, and by the careful watching of telescopes, a piece of a distant planetary system drifts past our sun and whispers to us about places we may never visit. Tonight, let us lean back, let the day's voices fade, and follow that whisper as far as our imagination and the data will allow. His story begins almost invisibly. It was first noticed as a faint point of light, a tiny wisp barely standing out against the crowded star fields of the southern sky. Discovery cameras gathered their nightly sweep. The survey pipeline flagged a moving dot, and human eyes, still the final arbiters of surprise, took a closer look. The object's position shifted from frame to frame, just enough to betray its motion. The orbit solvers went to work, and the numbers refused to fit the usual stories we tell about comets and asteroids. This path wasn't a closed ellipse like a long-period comet returning from our own distant Oort cloud. It was hyperbolic, an open arc that says, as plainly as a plot can say, "I am not bound to the Sunday." In human terms, it is the difference between a neighbor stopping by and a traveler from far away passing through town on a journey that began before we were watching. The telescopes named the Find 3I Atlas 3I because it is the third confirmed interstellar object we have observed, after 1I, Oumuamua in 2017, and 2I divided by Borisov in 2019, an extraordinary addition to a very small club of cosmic nomads. NASA Science +1. There is a practical geometry to its visit, and geometry makes a soothing kind of bedtime truth. Astronomers can say when and where the visitor will come closest to the Sunday. Their calculations show that 3I Atlas will make perihelion its nearest approach to our star around the 30th of October 2025, at a distance of roughly 1.4 astronomical units. That's a little farther out than Earth's orbit and close to the orbit of Mars, about 130 million miles, or 210 million kilometers from the Sunday. It will not swoop in tight enough to blaze into a spectacle for casual eyes. It will remain modest, a subdued guest keeping its distance. Its closest approach to Earth will also leave it well beyond our immediate neighborhood, on the order of 1.6, 1.8 AU. So there is no danger in its passage, no drama, just the elegance of celestial mechanics carried out far from harm. NASA Science +1. Before perihelion, its road threads the realm of the red planet. Models indicate a pass that places it tens of millions of miles from Mars in early October, a distant hello rather than a handshake, enough that orbiters there may try for a careful look, but far too distant for anything like a close-in encounter. For most of us on Earth, this will remain an event we meet through images and spectra rather than with our own eyes. The comet will slip behind the sun from our point of view, briefly hidden in the glare, and then reappear in early December, fainter, receding, and already beginning the long exit that its orbit demands. There will be no fireworks. The quiet is part of the story. Star Walk +1. What makes a distant fragment worth such attention is that it functions as a natural sample box from beyond the solar system. Every comet or icy body that forms around a star preserves, within its dust and ices, a memory of the environment where it coalesced. The temperature profile of its disk, the abundance of volatile molecules, the radiation bath of its young sun, the collisions that shook pieces loose. An interstellar visitor, like 3I Atlas, is a messenger carrying a foreign chemical dialect. When light passes through the gas and dust around it, the coma, that ghostly shroud that surrounds its nucleus-specific molecules, leave fingerprints called spectral lines. By measuring those lines in infrared wavelengths, scientists can reconstruct a list of ingredients and, from that list, infer something of the kitchen where the recipe was first mixed. Here, the observations are especially intriguing. Early sensitive spectra, most notably from the James Webb Space Telescope, reveal that the coma is unusually rich in carbon dioxide compared to water. In fact, the CO2 to H2O ratio, measured for 3I Atlas ranks among the highest recorded for any comet observed near the Sun, a signal that stands out from the statistical trend seen in familiar long-period and Jupiter family comets. Alongside CO2, observers have identified H2OCO, water, ice, dust, and even traces of OCS, carbonyl sulfide, each identification an extra syllable in the object's chemical accent. The coma appears somewhat asymmetric, with enhanced outgassing toward the Sun, suggesting patches of active terrain responding to solar warmth. All of this points to a nucleus, intrinsically rich in CO2, perhaps formed near the CO2 ice line of its birth disk, or processed in a radiation environment unlike our own backyard. Whether because water sublimation is suppressed or because carbon dioxide was abundant from the start, the balance tips decisively toward CO2. And in that tipping, models find new constraints. To imagine what that means, picture two kitchens making the same basic recipe. One uses more salt, the other more sugar. The final tastes are both recognizably the same kind of dish, yet different in ways that reveal something about the cook and the pantry. If comets are recipes of ices and dust, then 3I Atlas adds a new seasoning to our cosmic banquet. By comparing its spectrum to comets born here in our system, scientists can begin to sketch the range of conditions that produce planets and small bodies across the Milky Way. A high CO2 content can suggest formation in colder regions of a protoplanetary disk, where carbon dioxide can condense into ice more readily than water, or formation under different radiation and chemistry. These are not speculative metaphors, but pieces of a forensic puzzle. Carefully measured lines, emitted photons, and dynamical histories combined to reveal origin stories. The beauty for a bedtime mind is that the forensic details are quiet and exacting numbers stacked like smooth stones, while the picture they build is grand, a planet-making factory in a distant system, leaving a breadcrumb that drifted across the galaxy and, for a night or two, into our instruments. Because 3I Atlas arrived as a faint wanderer rather than a blazing show, our study of it requires patience and rigor. Observatories across the world pool their measurements. Photometry that tracks how its brightness changes with distance and viewing angle. Spectroscopy that reads its chemical fingerprints. Astrometry that refines its precise motion through space. Each dataset tightens uncertainty. How large is its nucleus kilometers across, or only a few hundred meters? How fast does it rotate? And does that rotation modulate outgassing? Is the flow from vents steady or sporadic? And does the coma carry large grains or mostly fine dust? Even small signals matter. In previous interstellar visitors, minute, non-gravitational accelerations from outgassing sparked debates about surface properties and internal structure. With better instruments, faster alert pipelines, and a global network of follow-up telescopes, 3I Atlas offers a richer, earlier look than we had for its predecessors, letting the community test competing models of formation and evolution, with a dataset that is, night by night, becoming beautifully overdetermined. There's history in this lineage of visitors. Oumuamua arrived without a visible coma, a dark shard with puzzling accelerations that launched years of discussion. 2I divided by Borisov swept in as a more classic comet, with obvious outgassing and a relatively ordinary composition. 3I Atlas seems to split the difference in its own way, clearly cometary, yet chemically tilted, modest in brightness, yet generous in information. Together they form a small but growing sample, enough to begin asking population questions. How common are such objects in the solar neighborhood? How many pass unseen every decade, their faintness hiding them from our surveys? What fraction are CO2, rich like 3I Atlas, and what fraction look more like typical Oort cloud comets? Each answer helps to connect the dots between protoplanetary disks across the galaxy and the raw materials that feed worlds. Beyond the data tables and plots, there is the human dimension. For a century, we've trained ever larger and more sensitive eyes on the sky. Survey telescopes that scan the heavens nightly, spacecraft that see in colors our eyes cannot detect, and networks that ping alerts worldwide when an unusual object pops into view. The discovery of 3I Atlas is a product of that vigilance, of software and glass and human curiosity arranged into a planet-scale listening device. It is humbling to remember that these tiny bits of rock and ice, flung out of their home systems during chaotic early epochs, can wander through the interstellar medium for millions to billions of years, and then, by mere geometry, pass within reach of our attention. The scale is almost absurd. Dust grains mixed with frozen volatiles endure unimaginably long journeys, and in a single sleepless night, someone at a console can catch their faint signature. Hold that contrast for a moment as you settle into the rhythm of your breath. Slow in, slow out. Think of the scale: the sun at the center, the planets in their lanes, and far beyond, the region where comets from our own cloud sometimes fall inward. Then think farther. Stars scattered through the thin disk of the Milky Way, each with its own retinue of debris. Somewhere out there, in a system that once had its own giant planets and its own jostling ice balls, a small thing was nudged by gravity, tossed outward, and set free. It coasted in the dark for an age, almost silent except for the low hum of interstellar radiation and the occasional dust grain pinging its surface. And then, this year, it wandered into our sunlight and began to breathe molecules shaking free and sparkling into a temporary atmosphere. That is 3I Atlas, not a loud visitor, but one that turns sunlight into a whisper we can read. The numbers themselves can be a lullaby. An astronomical unit, AU, is the average Earth-Sun distance. 1 AU is about 150 million kilometers. 3I Atlas will shave a little closer to the Sun than 1.4 AU, and it will keep well beyond 1.6 AU from Earth, which is a way of saying comfortably far. Light takes just over 8 minutes to cross 1 AU. At 1.4 AU, photons travel to and from the comet in something like 19 minutes. Meanwhile, the object cruises along its hyperbolic track with a speed that will peak near perihelion, then slacken as it climbs out of the Sun's potential well. We won't see it loop back. The curve is an open door that will not swing shut while any human alive today is still listening. If you enjoy small rituals, there is one you can perform on clear nights. Step outside and find a patch of sky that feels quietly yours. You won't see 3I Atlas with unaided eyes, but you can feel the architecture of its passage in the way the planets array themselves along the ecliptic, and the way the Milky Way drapes overhead like a scarf of old light. Somewhere within that arrangement, careful instruments are measuring spectral lines, slim fingerprints, where molecules bend and stretch in infrared colors. And from those lines comes a picture: CO, 2 tallies, far outpacing H, 2O, CO present but quieter, OCS, making a cameo, water ice scattering light as fine frost in the coma. The ratio of CO2 to H2O is a diagnostic. If you could write the chemistry of this comet as a fraction, CO2 would tower, H2O would be a modest denominator. It's not that water is absent, it's there, in vapor and in ice, but in the contest for dominance. Carbon dioxide is the unanticipated winner. That simple fact forces models to adjust. Perhaps the nucleus has shallow thermal penetration, preventing deeper water-rich layers from heating. Perhaps the topmost veneer is CO2 rich. Because of the chemistry of its nursery, perhaps both are true. Science welcomes such forked paths. Each offers a test. Behind the scenes, orbit computers continue to refine the comet's hyperbolic elements. Its eccentricity, comfortably greater than 1, its inclination, tilted and retrograde with respect to the planet's flow, its precise timing around perihelion. Even the Precovery images, older observations that happened to capture the object before discovery, may be folded into the solution, lengthening the observation arc and tightening the uncertainties. There's a quiet satisfaction in that, the way librarians feel when a misplaced volume is found and returned to the shelf. And in that satisfaction, a deeper calm, the sense that even when the universe arrives as a surprise, we have the means to situate it cleanly within our understanding. Once you know to look, the engineering of attention is everywhere. The Atlas survey that spotted this visitor was designed as a planetary defense tool, 4 small telescopes that sweep the sky for moving things that might one day matter to us. Most nights their finds are routine. Main belt asteroids, near-Earth objects that miss us by healthy margins, comets that glow politely and return to distant aphelia. But every so often the feed carries a point of light that follows a path only an outsider would take. A flag goes up, a note goes out. Follow-up observations pour in from amateur and professional observatories alike. The pipeline is global, almost musical in the way it passes themes from one instrument to the next. Discovery, confirmation, characterization, modeling, testing, each movement informed by the last. 3. iAtlas is a testament to that planet-wide vigilance. A reminder that we are, right now, living in an era of real-time cosmic listening. NASA science. If you're the kind of listener who likes to picture the hardware, imagine Webb's near spec pointing into a star-crowded field. Starlight filtered out. The comet's faint glow spread into a spectrum like a secret laid flat. In that spectrum, a series of dips and peaks, absorption and emission features, mark the vibrations of CO2, the rotational fingerprints of H2O, the telltale notes of CO and OCS. Each feature is tiny, measured in microns and millijanskis, but it is enough. Webb is sensitive to whispers. From that whisper, astronomers derive mixing ratios, outgassing rates, even directionality. A sunward lobe, where molecules stream faster, a nightside lull where the surface stays colder and quiet. Others on the ground add visible light photometry, polarimetry to gauge grain sizes, and high-resolution imaging that catches the coma's texture. What began as a point becomes a profile. What began as motion becomes a biography written in sunlight. The philosophical delight is that all this precision sits easily beside wonder. You can let numbers reassure you, perihelion dates, distances, signal to noise, and still allow your mind to drift outward into the story implied. A small ice rock, freed from its system by the nudge of a giant planet or the jolt of a collision, coasts through interstellar night. It encounters almost nothing for an immense span of time, then glides into the outskirts of a new star's gravitational field. As it falls inward, sunlight begins to do chemistry on its surface again. Cracks open, molecules stir. The coma blooms like a slow flower whose petals are atoms and grains. For a few months, the object acquires a voice we can detect. And then, as it rounds the sun and departs, that voice fades. Silence resumes. In between, we took notes. There are practical ripples too. Each interstellar object we characterize adds to population statistics. How many such wanderers pass within, say, 5 astronomical units of the Sun each year? With better surveys coming online, will we catch more before perihelion in time to mount focused campaigns? Could we ever intercept one, send a dedicated probe to fly by, or even to sample? The questions are no longer fantasy. Trajectory planners have run scenarios. Engineers have drawn up rough concepts. The time from discovery to launch is the hard part. For now, we do the next best thing. We gather a thorough remote sensing dossier while the traveler is within range. The archives that result: spectra, images, astrometry will be mined for decades, serving as benchmarks for the next discovery and the next. If interstellar objects are reasonably common, they likely play roles in planet formation and chemistry throughout the galaxy. Some models imagine them as seeds, nuclei that, when captured by a young disk, can act as condensation sites for local material. Others see them as couriers, moving organic molecules from one system to another, contributing a sprinkle of complexity wherever they go. These are not settled questions. They are the kinds of hypotheses that sharpen with data. And 3, I-Atlas, with its CO2 heavy character, gives the models a very specific constraint to meet. If a disk makes many objects like this, what does that say about its temperature structure and radiation field? If it rarely does, what exceptional pathway produced this one? In both cases, the universe becomes less vague. Let's pause and shrink our scale again, not to kilometers or microns, but to the human. Somewhere tonight, a graduate student is coaxing a difficult spectrum into shape, subtracting skylines, flattening fields, and checking calibration laps with the concentration of a watchmaker. Somewhere else, a team is writing a pipeline to cross-match observations from a dozen facilities, aligning epochs like beads on a string, so parameters can be fit and refit. These are the sleepers of tomorrow, their work tucked into archives that future readers will open with gratitude. And in living rooms and backyards, amateurs turn their telescopes towards star fields marked with red circles on finder charts. Most will see nothing but the field. 3 I-Atlas is too faint for small instruments under most skies, but the act of trying connects them to the project. The night sky is a commons. Even when we cannot see the current guest, we can watch the place where it is and feel the pleasure of sharing a sky that hosts things we are only barely able to know. Just as sleep comes in gentle thresholds, so does the exit from our story. After perihelion, as the comet rounds the sun, the outgassing will ebb. Dust released near perihelion will continue to trail along the orbit, a thin ribbon growing ever more diffuse. The nucleus, having warmed and vented, will cool again as it heads outward. Gravity will not call it back. The hyperbola carries it away. It will cross the realm of the outer planets, pass through the cold confetti of the Kuiper belt, and then the darker emptiness beyond. Its next encounter of note may not be for millions of years, and even then it may only be a slight nudge, a statistical whisper rather than an event. The universe is a patient editor, and yet a trace remains. The data this visitor leaves behind, spectra, astrometry, images, will persist in our repositories. There, its CO2 rich signature becomes a line in a catalogue, a figure in a paper, a footnote in a textbook a decade hence. A future student might compare it with the chemistry of a newly found planet's atmosphere and notice a rhyme. Or a future mission designer might use its trajectory as a test case for an intercept concept study. In that sense, 3 I-Atlas achieves a small immortality. It etches itself into our collective memory not as a spectacle, but as a datum with edges crisp enough to be picked up and used. That is a lovely kind of permanence, modest and durable. If you find yourself wondering whether such encounters are portents of larger mysteries, keep one steady thought in mind. The universe is rich in regularity and surprise in equal measure. 3 I-Atlas is neither proof of life elsewhere nor evidence of anything supernatural. It is a natural outcome of dynamic planetary systems, of physics and chance. Still, its passage touches something deep, the sense that our world is not alone in a sterile emptiness, but participates in a lively galaxy where matter moves, exchanges, and occasionally delivers pieces of one cradle of worlds to another. For children, for dreamers, and for young scientists, that idea is generous. The cosmos is not merely backdrop, it is a network of stories. And sometimes one of those stories arrives at our doorstep, written in a hand we can learn to read. So as your eyelids grow heavy and the shoulders of the day relax, picture for a moment the faint wisp of light that was noticed in the southern sky. A visitor named 3I Atlas, carrying the slow handwriting of chemistry and history. Imagine telescopes waiting like careful readers, intent on a fragile manuscript, passing the letters of ice and dust to reconstruct a sentence about a place unimaginably far away. Let the technicalities that it comes nearest to the sun around October 30, that it remains distant from Earth, that its coma sings in the voice of carbon dioxide be part of the lullaby. The precision of numbers woven into the fabric of wonder. Breathe out, and let your mind drift along the slow arc of this traveler as it moves onward through the galaxy. Remember that even the faintest light can bring a message. The universe is larger and stranger and kinder than we sometimes imagine, and every so often it sends a traveler to remind us. Good night from Bedtime Universe. All right, the next story we settle into is about deep time, the faint hum of cosmic interconnection, and a mystery that only began to unfold when everything in the outer solar system aligned in a way no physicist thought possible. This is the tale of Project Lachesis and the unsettling whispers carried on the solar wind during the solstice of Eridanus. Part 1. The arrival of the rogue shepherd. In the cold, perpetual darkness that lies beyond the Kuiper Belt, past the final, lonely sentinels of ice and rock, a celestial body was moving. It wasn't a comet, pulled by the sun's fierce gravity. It wasn't a Kuiper Belt object, tethered to the ecliptic plane. It was an object catalogued as Xylos, a rogue exoplanet, roughly the mass of Mars, traveling on an impossibly shallow hyperbolic trajectory that was bringing it into our Oort cloud, yet not towards our Sunday. Imagine the Oort cloud, that vast spherical shell of icy debris as the very edge of our sun's dominion, a shimmering, silent boundary between the known and the interstellar void. For millennia, it has remained undisturbed, a frozen record of the solar system's birth. But Xylos, this quiet, dense traveler, was slicing through it like a ghost ship through heavy mist. The scientists at Project Lachesis, operating out of a subterranean complex in the Atacama, initially dismissed it as a statistical anomaly. Xylos was too dense to be a captured object, too distant to be a planet, and its velocity was subtly wrong. It was moving too slowly, yet with an inexplicable rotational frequency. Dr. Elias Thorne, head of the project, often described it to his interns as a silent shepherd, because its passage wasn't causing gravitational chaos. Instead, the distant cometary bodies ahead of it seemed to be settling, their orbits becoming unnaturally orderly, as if drawn into a state of subtle rotational peace. This state of uncanny quietude was the first clue. Gravity, we understand. Chaos, we anticipate. But this induced cosmic order suggested a force that was less about brute mass and more about resonant fields. Xylos was not just moving through space. It was interacting with the fabric of space-time in a way our current models could only vaguely predict, leaving a wake of unnatural stillness in its path. We often forget that space is not empty. It's a plasma-infused medium, a vast electrical conductor, and Xylos seemed to be tuning it. Part 2. The silence of the Sentinel. Roughly 2 months after Xylos's initial detection, and just as it entered the inner Oort cloud boundary, our attention was wrenched toward the very frontier of interstellar space, Voyager 1. The oldest, loneliest messenger humanity has ever launched, now traveling through the turbulent, magnetically active realm of the interstellar medium. For decades, Voyager's plasma wave subsystem had been sending back a steady, albeit faint, recording of the density and magnetic pressure outside the sun's influence. It was the sound of space, a low, oscillating hum. Then, at 3:17 UTC on the morning of the solstice, the hum stopped. Not a sudden catastrophic failure, which would have indicated a micrometeorite strike or power loss. Instead, the data stream showed a perfect, complex harmonic spike, a signature so mathematically pure, it initially triggered a data corruption warning. The spike lasted exactly 4.83 seconds, and then the plasma wave detector went dead. Silence. A digital void that stretched for 3 hours before the system miraculously rebooted, only to report normal but inexplicably weakened background noise. Dr. Thorne, a man who rarely used adjectives stronger than noteworthy, called the initial 4.83-second burst a signature of deliberate compression. The energy was not random. It was structured, like a perfect chord struck on a gigantic interstellar string. It suggested that a colossal wave of structured energy, perhaps an extremely low-frequency electromagnetic pulse, had washed over the probe. A wave that carried a pattern, not noise. What was the common thread? Xylos was still hundreds of billions of kilometers away from Voyager, yet the moment of the signal's emission was calculated to have perfectly intersected with the time Xylos crossed a major heliopause boundary relative to the plane of the ecliptic. It was a conjunction of events separated by unimaginable distances, yet connected by a single, terrifying timestamp. Part 3. The geometric veil of Saturn, the third, and perhaps most beautiful piece of the puzzle, appeared orbiting the ringed jewel of the solar system, Saturn. Saturn's rings are a masterpiece of chaos and gravity, billions of particles of ice and dust, constantly colliding, shaped by the push and pull of its many moons. The ring system is dynamic, complex, and utterly predictable under the laws of physics. However, a global amateur astronomy collective, monitoring Saturn's rings for the annual Mimas resonance shift, captured something unprecedented. A new, perfectly defined, faint K-ring had formed in the outer F-ring zone. This ring was not a cloud of particles, it was a structure. It possessed a lattice-like geometry that was visible only under specific infrared spectrums, forming a series of non-Keplerian shapes, squares, tetrahedrons, and perfect hexagons that rotated not by gravitational rules, but by an internal, synchronous frequency. The material forming the K-ring was not typical water ice. Spectroscopic analysis suggested charged silicates infused with rare earth plasma, and its formation was instantaneous, not gradual. It appeared overnight, on the very day the Voyager signal went silent. This geometric construction, defying the mathematics of orbit mechanics, suggested an active manipulation of the magnetic field lines. Saturn is a giant magnetic dynamo. Its rings are essentially vast plasma screens. The K-ring was acting like a colossal circuit board, holding impossible shapes in place through an unseen electromagnetic framework. Thorne theorized it was a triangulation point. The rogue planet Xylos, the charged particle field of the Oort cloud, and the magnetic field of Saturn were not three separate entities. They were nodes in an ancient, forgotten network. Part 4. The inevitable alignment. The ultimate realization lay in the calendar. The solstice of Eridanus. This wasn't a modern alignment. It was an ancient, calculated celestial moment when the center of the Milky Way galaxy, the plane of the solar system, and the most distant star in the Eridanus constellation that the ancients could track, all fell into a near-perfect 33.3-degree angle. This particular angle, according to obscure astronomical texts recovered from a forgotten observatory in the Himalayas, was called the angle of zero entropy, the point where the flow of cosmic energy achieves maximum coherence. Every event that had transpired, the calming field around Xylos, the perfect harmonic spike from Voyager, and the geometric formation of Saturn's K-ring, had been timed not to the modern Julian date, but to this ancient, almost mythic solstice. The hypothesis: what if the solar system, with its planets, its magnetic fields, and its plasma sheaths, was not merely a mechanical clockwork, but a vast, organic, resonating instrument? And what if Xylos wasn't a rogue planet, but a key, a massive, natural tuning fork, designed to enter a specific region of the Oort cloud at a specific time, to induce a coherent magnetic field resonance that would travel through the interstellar medium, strike the Voyager probe at the perfect instant, and finally, activate the solar system's primary magnetic node, Saturn, to display a geometric signal. The signal wasn't a radio transmission. It wasn't a light pulse. It was a structure. A temporary, perfect architectural arrangement in the plasma of the rings. A message written in the language of pure physics and geometry, lasting only a few weeks until the solstice alignment broke. The whispers carried by the solar wind were not random. They were the gentle hum of this cosmic mechanism coming to life after eons of silence. Epilogue. The deep hum of connection as we watch the solstice pass and the K-ring slowly dissolves back into the random chaos of Saturn's dust. We are left not with answers, but with a profound sense of awe. The events suggest a vast interconnected ecology of energy, where the movements of a single rogue body can ripple across light years and awaken ancient, dormant physics. It forces us to reconsider what coincidence truly means in a universe defined by laws we have barely begun to scratch the surface of. Perhaps the greatest lesson from Xylos, Voyager, and Saturn's geometric veil is this: we are not observers in a cold, silent universe. We are living within a massive, intricately wired machine that occasionally, gently, and with infinite patience, sends us a message written in the language of stars and magnetic fields. Rest now. Let your mind drift with the slow, resonant currents of the cosmos. The universe is awake, and its humming is the softest lullaby. Good night. Okay, let's go to the next story. Close your eyes if you like, or keep them softly open. Let them fall into the gentle half-light, where room and sky breathe together. Breathe once, slowly, as if inhaling a secret the universe has been whispering for billions of years. Breathe out. Release the day, like a small stone dropped into a wide, patient pond. Tonight we will walk, softly and carefully, along the edges of wonder. Imagine first a single point of light, far beyond the reach of your fingertips. It hangs in the vast blue-black, a patient ember in the dark. That light is an ancient letter, written in photons and carried for eons across loneliness and time. Each photon is a tiny messenger telling a story of clouds collapsing, of pressure building, of eventual fire. It tells us how a star was born. We begin in a nursery, not of cradles and lullabies, but of dust and quiet gravity. In these vast stellar nurseries, clouds of hydrogen breathe and sigh. They swirl and settle, a slow, graceful choreography. Regions within them grow heavier, tiny seeds of density that call to each other. Gravity, subtle and relentless, draws them closer until warmth blooms in the heart of a contracting cloud. At first, there is only the hush of atoms colliding, but then the hush becomes a murmur, and the murmur a steady hum, the birth heartbeat of a star. Picture that newborn star like a candle cupped against a blizzard, fragile yet defiant. It begins its long work of turning matter into light, forging heavier elements in its crucible. Over millions or billions of years, it is both creator and instrument. Carbon, nitrogen, oxygen. These are not gifts dropped from nowhere. They are the labor of stars, the slow alchemy that stitched the periodic table into patterns that would one day be read by biology. Drift now to the patient geometry of planets. The protoplanetary disk that surrounds a young star is a slow-turning carousel. Dust grains stick like shy dancers, finding partners. Pebbles accumulate to rocks, rocks to boulders, and boulders by a kind of stubborn fortune become worlds. Each planet falls into its lane, some near and scorched, others distant, wrapped in the deep sleep of frozen gases. Some catch thick atmospheres and wear them like robes. Others are bare, their scarred surfaces reading like old maps. Listen. The language of geology speaks in storms and tides, in continents wandering on oceans of rock, in the patient corrosion of winds. On some worlds, water pools and Waits rivers tracing the skin of the planet, oceans breathing with the slow rhythm of tides. Where chemistry and liquid meet, curiosity becomes possible. Where energy is steady and ingredients meet for long enough, chemistry can begin to take the first timid steps toward biology. Life, when it appears, is not an announcement so much as a very quiet persistence. It is the universe learning to know itself through rearranged atoms and the improbable poetry of replication. Let your mind stroll now beyond the pale neighborhood of a single star to the wider assembly's binary stars that spin around each other in an intimate conversation. Systems where planets chase one another in complex arcs, moons that steal the stage and then return it. Imagine a night sky from the surface of a world that circles two suns. Dawn here and dusk there, shadows overlaying and unraveling, as if the universe were practicing a gentle illusion. Or imagine a planet where the seasons stretch for centuries, and an entire civilization learns patience from a slow, wandering orbit. We can come closer, closer than even the crescent of a moon, and meet comets. Comets are wayfarers, icy, ancient, carrying the scent of the outer reaches. When they approach a star, heat teases their frozen past into jets of dust and gas, creating a tale that points away, like a memory streaming behind a moving soul. Some comets have visited the young Earth, delivering water and organic molecules, small serendipitous couriers, possibly responsible for nudging chemistry toward life. They are reminders of how the universe keeps its treasures in remote vaults until the right moment. Now, allow the scene to widen. The galaxy is not a static painting, but a slow, turning ocean of stars. Our Milky Way is a disk of countless lights, an elegant swirl observed edge-on as a delicate line of soft brightness, or seen from within as a band of spilled sugar across the night. The galaxy's spirals are arms roots of ongoing formation, places where gas is funneled, compressed, and nudged into new generations of stars. At the center sits a quiet storm, a supermassive black hole, not a hungry villain in a storybook sense, but a sculptor whose gravity molds the dance of millions of suns. Black holes are not only endings, they are thresholds. Their gravity warps both space and time, bowing light as if the fabric of reality were a soft sheet. When a black hole feeds, it can make light brighter than entire galaxies, an irony that reminds us how extremes are sometimes necessary to create beauty. Around many black holes, matter swirls in a furious incandescent maelstrom, jets of particles leaping outward like fountains that pierce the dark. The mathematics that describe such objects are both austere and wondrous, a vocabulary where infinity and smallness meet. Think for a moment about the scales we talk about. Atoms to planets, planets to galaxies, galaxies to clusters, and then to the cosmic web. Between galaxy clusters, filaments of gas and dark matter trace a pattern like frost on a window. Dark matter, an invisible presence, holds the web taut, a scaffolding without which galaxies would not gather. Though we cannot see it with our eyes, we sense its gravity by watching things move as if pulled by invisible hands. There is humility in that. Much of what shapes the universe is one step removed from our senses, and yet is no less real. Time itself carries a story. The cosmic microwave background is a faint afterglow of the universe's earliest visible chapter, a whisper from when the universe was just a few 100,000 years old. It is cool now, a mere 2.7 degrees above absolute zero. But it is a map, a photograph of the infant cosmos, with tiny fluctuations that seeded everything that followed. To hold that image in your mind is to understand that even the largest things started as the smallest differences, tiniest ripples that eventually grew into vast structures. Picture the cosmic timeline like an old patient book. The first pages are quick and feverish. Inflation, a sudden stretching that smoothed space like kneading dough. Then, atoms formed, light untangled from matter, and a dark age fell long and silent until the first stars lit tiny lamps that pushed back the gloom. Galaxies assembled, merged, and spun off new generations of stars. Planets formed from the debris left in the aftermath of these cosmic negotiations. In this unfolding, humanity appears very late, an afterthought in the second-to-last paragraph, and yet, in the human mind, a universe of meaning ignites. Let us visit one small chapter in which curiosity itself evolves. Consciousness. Somewhere in the long history of Earth, early cells invented a trick replication with variation, and then, over eons, nervous systems learned to sense. Brains are storytellers. They knit signals into patterns and name them. Consciousness is an emergent candle, lit by complexity, sustained by exchange, and flickering with memory. It is in this candlelight that we ask why and how, and in asking, we create narratives that fold the cosmos back onto itself. Imagine now an observer standing at the edge of a cliff beneath a trembling aurora, or a night watchman on a ship gazing at the stars smeared with meteor trails. The same processes that cook the insides of stars also create the copper in your phone camera, the oxygen in your lungs, the metal in a bridge, the calcium in a tooth. These are all descendants of ancient stellar furnaces. There is a soft, almost ineffable intimacy in that. The universe gave us, over long patience, the very elements that make selfhood possible. We can also sense the fragility of home. A planet's atmosphere is a delicate blanket. It can warm gently under a benevolent star and sustain richness, or it can be stripped away by flares and winds, leaving raw stone. Small differences in chemistry, rotation, or magnetic shields can mean the difference between a world teeming with potential and one that remains mute and barren. The history of planets is a study in chance and contingency. Local weather, global catastrophes, rare impacts, the ephemeral vicissitudes that shape long-term trajectories. Turn your attention now to communication across distances. Light is a faithful courier, but it travels at an upper limit. Signals sent across interstellar space take years, centuries, or millennia to arrive. Even at light speed, messages are delayed by the tyranny of scale. If someone on a planet 500 light-years away shouts into the dark, their voice is a letter that will arrive here only 5 centuries from now. That slowness teaches humility and patience to any mind that imagines sending greetings. Consider how we listen. Our instruments extend senses. Radio telescopes tune to the faint hum of hydrogen between galaxies. Spectrometers unweave starlight into colors and reveal composition like detectives reading fingerprints. When we find a spectrum with telltale signatures, water, methane, oxygen, we do a kind of forensic archaeology across time and space. We cannot visit many of these places. Instead, we learn to translate the light they send, to read whispers of chemistry and motion, and to infer landscapes from small, indirect clues. There is also the poetry of scale in motion. Galaxies collide not as catastrophic bangs, but as slow, majestic ballets that stretch across millions of years. When two galaxies meet, their stars mostly pass like ghosts, but their gas clouds crash and ignite bursts of star formation, new lights born from the turbulence. In the far future, our Milky Way will kiss Andromeda in such a dance, a slow merging that will change the map of the night, but will not necessarily be an apocalypse for individual systems. Time grants the universe a kind of patience we cannot fully fathom. Let us touch, briefly, on endings and beginnings folded into one. Stars of certain masses end their lives with a final flourish. They swell into red giants and drop outer shells that smell of future gardens, planetary nebulae, whose glowing rings are nothing less than stellar farewell notes. Some massive stars go out as supernovae. They explode with a brightness that can outshine entire galaxies for a while, scattering heavy elements into the void. These explosions are fertile. They pepper the interstellar medium with the seeds for future planets and life. The iron in your blood was once inside a star that died in fire. And then there are rarer endpoints. Neutron stars compacted into the mass of the sun, but squeezed into a city-sized sphere, spinning so fast they sweep beams of radiation across space like distant lighthouses. When two neutron stars merge, they ring the cosmos in gravitational waves, ripples in spacetime itself. These ripples are like the faint tremors of a gigantic bell, small on our scales but monumental on a cosmic ledger. We have learned to hear them, to listen to spacetime, and in doing so, we have opened a new sense. Now imagine, for a slow moment, a distant sea, where bioluminescent organisms light up like stars in miniature. Each little flash a private signal, an invitation, a memory. On some exoplanets, life, if present, might glow under active skies, or it could be hidden within subsurface oceans under a frozen crust. Moons like Europa or Enceladus, in our own system, hide oceans beneath icy shells. There is something deeply consoling about water kept warm and dark for aeons, about the patient possibility contained in enclosed seas. If life exists elsewhere, perhaps it is quiet, tucked into corners where chemistry can be steady and undisturbed. Let your thoughts wander to civilizations, which may exist as brief candle flares along a long timeline. The technological curve of a species could rise quickly and fade due to self-made or natural disasters. It could also plateau into a sustainable, quiet stewardship. We do not know. We only know our own species' late curiosity and the sudden brightness of our signals leaking into space like dandelion seeds in a wind. Radio and light-based signals expand outward, thin and faint, like footprints in powder snow, detectable at a distance if someone is both listening and clever enough. There is comfort here too. Loneliness on cosmic scales does not mean emptiness. The cosmos is full of patient processes. Life and intelligence, if rare, may be spread like scattered campfires across an enormous plain. And perhaps the act of knowing, of looking, measuring, imagining, binds us into a community with the rest of the cosmos. In studying stars and particles, in parsing spectra and building telescopes, we cast ourselves as students in a grand school. As you listen, either with your ears or with your mind, feel the rhythm of the universe as a lullaby of durations. A human lifetime is a handful of breaths compared to geological ages, and geological ages are a blink beside cosmic epochs. Yet within a single heartbeat, we can hold awe, grief, curiosity, and love. These human scales are not failures of perspective. They are the universe experiencing itself in a compact, fervent form. Now, imagine returning home, descending slowly from the bright cathedral of the galaxy, through the still, cold arms of interstellar space, past the commuter belts of comets, past the warm glow of a friendly star. You approach a tiny blue planet, the home you know. From orbit, continents are soft petals and storms curl like calligraphy. Cities are small nodes of light, patterns of habit and story woven together. On one such night, someone looks up with an ancient sort of yearning, recognizing in the dots above both estrangement and kinship. To end, consider this quiet, generous truth. You are made from the same elements as the stars, and those elements have traveled cosmic distances to arrive, patient as rain, into your bones. Your thoughts are shaped by molecules forged in fire. Your curiosity is a continuation, an echo of the processes that stoke stars and fold galaxies. In that sense, the cosmos is not merely something outside, it is an inheritance and a companion. So let tonight be ordinary and extraordinary at once. Let the soft knowledge of distant light settle in like warm dust. If sleep comes, let it be gentle, like the slow drift of an orbit. If your mind wanders, let it wander along the spiral arms, where new stars are still being hatched. Tomorrow, when you open your eyes, the world will feel familiar and newly strange, and you will carry with you the hush of long distances, the patient grammar of the universe, and finally, a closing image. A small child on the threshold of a house, holding a lantern. The child is not yet sure what stories will come, but they are learning to read the sky. The lantern casts a gentle circle of light, and, within it, the child's face is full of person-sized astonishment. Outside that circle unfolds a darkness so wide and generous that it invites stories rather than denies them. Walk now into that small, safe pool of light. Breathe, and let the vastness sing you slowly into rest. Good night.